We're going to look at polynomial functions today. The first problem, you can see this little picture of a honeycomb here. The cross section of a honeycomb has a pattern with one hexagon surrounded by 6 more hexagons. Surrounding these is a third ring of 12 hexagons and so on. The total number of hexagons then in the honeycomb can be modeled by the function given here, where R is the number of rings and F at R is the number of hexagons. Find the number of hexagons when R equals 4 and when R equals 12. So how many, basically when they want to know what is R, how many hexagons when R equals 4 means how many hexagons are going to be total when you include the first 4 rows. So what we got to do is take this value of 4, R of 4, and plug it into that function and see what you get. So F evaluated at 4 would be 3 times 4 squared minus 3 times 4 plus 1. So we plug in 4 everywhere we see an R in that function. Now it just basically becomes a calculator problem. So on your calculator, you can enter in that function and you can evaluate it. So we got 3 times the value 4 squared minus 3 times 4 plus 1. And the answer is 37. Now, another way we could do this with the calculator too, since we also have to, they also asked us to find how many total hexagons when there's 12 rows, is instead of entering it all again, we could go into the graphing part and enter in the actual function itself. So 3x squared minus 3x plus 1. So we've entered in that function that's given there. And then you can look at the table of values. So you can go to your table function on your calculator and bring up all the values. You can see if we go to 4, you can see the number we just got, 37, is there. If we keep scrolling down, we could see what it is at 12. And it looks like when f is 12, you get 397. So the function evaluated at 12 is 397. And that's a nice part about functions is once you have the function entered, you can pull up any value relatively quickly. Okay. All right, some terms that we're going to be talking about today and throughout the rest of the chapter. Polynomial in one variable. That means only one variable in the polynomial, kind of what it says in the original title there. Also, it means no variables in the denominator of a fraction. So all our polynomials are going to be in the numerator. The degree of a polynomial, we've talked about this term before. It's the largest degree of any one monomial in the polynomial. Largest degree of a monomial in the polynomial. What's the biggest exponent you see on one of the variables? The last term, leading coefficient. The coefficient of the term with the largest degree. And recall that coefficients are the actual numbers in front of your variables. So what's the number or coefficient of the term with the greatest degree? So we're looking for what's the number in front of the variable with the largest exponent or power. So these are all terms that we will talk about throughout the notes and throughout the rest of the chapter. All right, let's use that in some of these examples here. So on this first one, it wants us to state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Okay, so let's check number 1. Do we have only one variable? Let's see, yeah, x, yes. We only have x in all our terms. It's okay to have just a constant term here, this -9. That's kind of like x to the 0 power, so that's okay too. So is this in one variable? Yes, this is in one variable. The next part of the problem wants us to state the degree. Remember, degree is the biggest exponent. So if we look at our exponents here, we have 4, 2. If there isn't one, that's 1. And this would be, like we said, x to the 0. So what's the biggest degree? The biggest one we see is 4. So this is degree 4. So our biggest power is 4. It's degree 4. All right, last thing they want us to list, what is the leading coefficient? So our leading coefficient, that's the number in front of the biggest power, or the biggest degree, which is this term right here. So what is the number in front of the coefficient? It would be 7. 7 is the number in front of the term with the biggest degree. All right, number 2, they want us to do the same thing. Let's check first, is this one in one variable? Well, we see x, we get to the second term, x and y. This one is not in one variable. And the reason, we have both x and y. So that one is not in one variable. All right, let's check our last one out here. Our last one, equation over here, expression over here, 7x to the 6 minus 4x cubed plus 1 over x. Is this one in one variable? It does only have x, but if you check out our last term here, the x is in the denominator. We said when we were looking at our notes, it's in one variable. That also means no variables in the denominator. So this one is not one variable because variable in the denominator. So anytime there's a variable in the denominator, then we say it's not a a polynomial in one variable. All right, these next problems are some function ones, and they want us to evaluate the functions at a certain term or certain numbers, or in this case, variables. We did that honeycomb problem we did right away, we were plugging numbers in, but now that we're plugging in polynomials into another polynomial. So on number 4, they want us to see what is the function at b squared. So what we have to do in this is everywhere we see an x, we need to plug in b squared. So f at b squared is going to be equal to 2 times, we're going to have to plug something in for x there, plus 3 times, there's another x, we're going to plug in something there, minus 1. So everywhere we see an x, we're now replacing that with b squared. Now we want to simplify. Simplify. On this first one, anytime you got a power to a power, we know we multiply that together. So that would equal 2b to the 4th power plus 3b squared minus 1. We can't simplify this anymore. There is no like terms. That's our solution. That would be our solution. All right, let's try number 5. On number 5, same thing. They want us to replace all the x's with c plus 2. This one's also a little different because you can see there's also a 2 here, which means they want us to multiply our function by the value of 2. So this one is going to equal, if we're going to do 2g at c plus 2. Everywhere we see, well, first we're going to multiply the whole thing by 2. And everywhere we see an x, we're going to replace it with c plus 2. So we have x. We're going to replace that with c plus 2. There's a power of 2 on there, minus 4. All right, now we got to keep simplifying. Parentheses, we got to do parentheses first, and it's being squared. So that means anytime something's squared means we have 2 of them. We got c plus 2 times another c plus 2. All right, so what do we got to do there? That's where we're going to have to distribute. Use that FOIL method to simplify. So we got c times c, which is c squared. C times 2 is 2c. 2 times c is another 2c. 2 times 2 is 4. And then we still have this minus 4 that we've been carrying through. Now we look to see, can we, is there any like terms that we can put together? Absolutely. These two c's we can combine together. 4 and negative 4 we can also combine together. The 4 and negative 4 are going to combine to be 0. So what we're left with is c squared plus 4c. The last thing now, distribute that 2 that we've had in front the whole time, and we got our answer. So the final polynomial would be 2c squared plus 8c. So if you're doing functions with polynomials, you plug those in as you go. All right. On the back, you see they show some graphs of polynomial functions. We're going to be looking at these throughout the rest of the chapter. The degree of the polynomial tells you a few things. One thing is the number of zeros that the function has. And we're going to be talking about zeros. Zeros is kind of the number of times it passes through the x-axis. So you can see a degree 0 never passes through the x-axis. Degree 1 passes through 1 time. Degree 2 passes through 2 times. Degree 3 passes through 3 times. Degree 4, 4 times, and etc. So the degree tells you how many zeros you have. Also, another thing down here, it also tells you something about the number of times it changes direction. The degree will tell you that too. Degree 0 never changes direction. You can see it's a straight line. Degree 1 also does not change direction. It's a constant increase. Let's look at degree 2. How many times does degree 2 change directions? Degree 2 changes directions 1 time. There's 1 change in direction. A degree 3 one changes. There's a change in direction here, change in direction here. This one has 2 change in directions. Degree 4 has 1, 2, 3 changes in direction. So what do we see about the degree and the number of changes in direction? Anytime you have a degree, doesn't matter what the degree is, the change in direction will always be 1 less than the degree. So changes in direction are always 1 less than the degree. Change in direction will always be 1 less than whatever the degree of the polynomial is. So if you have a degree 10 polynomial, you'll have 9 changes in direction in that graph. The last thing we're going to talk about with these graphs is even and odd. Even degree polynomials always end up going in the same direction. You can see from our graph here, if you look at degree 2, the ends of the graph both end up going in the same direction. Same with degree 4, they go in the same direction. Degree 6 would be the same thing. Odd functions do something different though. The ends go in different directions. You can see degree 3, one side's going up, the other side's going down. Degree 5, one's going up, one's going down. So degrees that are odd go in opposite directions. All right, what we're going to talk about tomorrow is a little bit more stuff with these graphs of polynomials, and we'll continue then.